Real quick, I'm going to go through what we lectured in week 2, technically week 3 of the course, and just going to review a little bit more about what I was trying to show in the class, especially the differences between executing AlphaFold2 on the Grace cluster here at Texas A&M, either in the monomer or multimer model. Right, so this is going to be just hopefully a short video kind of showing you how I approach troubleshooting and how I may work through problems as they arise, right? So I've got my VPN configured, so I'm going to go ahead and shell in to Grace, right? Do the old two-factor authentication, and we will arrive in our home directory, right? We'll all see this warning. Just to reiterate, right, when you first secure shell into any of the HPC clusters on campus, you'll arrive in your home directory, right? You have two directories, or disks, sorry, and that's home and scratch, right? So the easiest way, again, you should really never mess with any files in your home directory unless you absolutely know what you're doing. So the first thing you always want to do is cd into your scratch directory, right? Right, now if we check with print working directory, or PWD for short, we'll see we are in our scratch directory. Okay, go ahead and clear the screen. I'm also going to make this a little bit bigger so it's easier to see. Right, so if you look, I have a lot going on here, so I'm just going to cd into my class folder directory. Right, and you'll notice that I have quite a bit going on here. Right, so I'm going to make a new directory called tutorial. I'm going to cd into it, just like if I was starting brand new and fresh, ready to run AlphaFold2. So, right, you'll notice that there's nothing in here, right? So the easiest way to at least get a starting script for AlphaFold is actually through their wonderful templates program that HPRC has curated for us called GCA templates, right? Press enter, it should open us up to what's called Bioinformatics GCA templates. Right, and you have a lot of options here, and I highly recommend you kind of go through and explore everything that's available to you that's really already been pre-compiled for you and is essentially ready for you to use outside of changing a couple of variables in each script. But today, we're going to focus on protein tools, right? So 8, we're going to have two options. We're going to either annotate protein sequences, which we're not doing, though it is a very useful tool if you ever continue with this predicted structure work in your own research. Instead, we're going to look at predict protein structure, right? So issue the number 2, enter, and then we have a couple of options. We're going to go with the most recent version of AlphaFold that we have available, right? So 6, and we only have one option out here, right? This is the only script that's written. It's for the A100 GPU monomer, right? So 1. It's going to ask, do you want to copy script to the current directory, being the current directory you issued the GCA templates command into? The answer is yes. It's going to say, hey, be sure to do the following. Read the software manual. Really, really important that you always do that. And add, adjust, remove command options as needed, right? So, right, if we clear this, and look, we now have a job script called run AlphaFold underscore 2.3.1 monomer grace sh, right? There's a couple of things we need to change here. So first, I'm going to show you how I would edit the script to run on the CPU only nodes and run the monomer PTM model, right? So I'm going to use Vim, which is a text editor in line with terminal. There's nothing stopping you from downloading this to your computer, editing it in your favorite text editor, and then re-uploading it, right? But I'm just going to do it in Vim for simplicity's sake. Right? There's a couple of things. So first, I'm going to show you the steps I take to remove the GPU settings that are inherently built into this job script so that it only runs on the CPU nodes. The first things we need to do is remove this sbatch command. Right? This is one of our directives that lets the Slurm scheduler know that we're requesting a GPU and specifically requesting the A100 GPUs. Right? So in Vim, without editing, if you just press the letter D twice, that'll delete whatever line your cursor's on, right? So pretty simple. The next thing I want to do to make sure this doesn't run on a GPU node, right? So I've removed the request for a GPU node, but you'll see in the line where we execute the singularity command, specifically there's this --nv. This means, hey, use NVIDIA GPUs. We don't want to do that. So we're going to just remove that command, right? Pretty simple. So it should just read singularity exec and then this command still stays, right? So this is issuing a singularity. It's pointing to the container that contains AlphaFold2's program, and then we're issuing the normal commands we would to run AlphaFold, which is Python, and then the location of the run AlphaFold dot. Run the AlphaFold.py. I copied an extra thing here, so I'm gonna go ahead and remove that. Copied a lot of stuff. Ooh. Right. Okay. All right. So singularity, execute the location of the container, and then the portions of this command to actually execute the software we want to do. Next thing we also want to change is this optional parameter called use GPU relax. Remember, since we have told the Slurm scheduler that we don't want a GPU node, it's going to throw an error when if you were to execute this as is. It's going to tell you, oh, you've said to use GPU relax, but we can't find a GPU. And so it's going to get like, I believe it'll get all the way through your job and then stop at the very end when that flag becomes relevant. I believe it might stop earlier, but just to be safe, we're going to enter the command false. Right? This is true by default, so we're going to tell it it's false. Okay. Next thing we're going to remove is this job stats or this ampersand sign. This was built into the script to do some benchmarking. It's not relevant to what we're going to do in class, so we can go ahead and remove it using that same quick shortcut, pressing the character D twice. We're going to do the same thing for job stats, right? So let's just cleaning up this a little bit, right? And then the next thing I would do is edit my protein.fasta variable. So this is just saying, hey, where can I find in your Scratch directory the FASTA file that you want to predict the structure for, right? So like I've done in class, I'm just going to issue the name of the FASTA because I always execute these job scripts and the location in the same directory as the FASTA file. So I'm just going to call it protein.fasta, keep everything simple. Right, now if I was doing a monomer prediction of a protein that does not have a structure deposited in the PDB, meaning I've gone and searched and checked to ensure that there is not a structure in the PDB, I'll leave the max template date as this. Importantly, right, ideally you'd want to set this to the current date that you're running it at. Right, and that would be if you were pulling updates for these like 5.6 terabytes or 3.4 terabytes of data as they get updated, monthly if not weekly. We don't do that on Grace because that would require a lot of upkeep. So the versions of these databases were released during 2.3.0 and have not been updated since. So you can just leave this max template date as is. Now, if the structure I was predicting I knew had a corresponding traditionally elucidated, whether it be X-ray crystallography, cryo-EM, or NMR structure, I would change this max template date to be before the deposited date in the PDB, right? And you can find that on the PDB's website. Next thing, right? When we initially ran this, we just ran the monomer model, right? Which is fine. It's actually great. But we also want to start to compute and start to probe and analyze the predicted aligned error. And in the monomer model, the only way you can do that is if you run the monomer model, specifically the monomer underscore PTM. Right? If you look right here, right, we see we have 4 different models. Monomer CASP14, the actual model that was used during the CASP14 competition, and then the 2 that you'll primarily always use are the last 2, monomer PTM and multimer. Right? Monomer PTM if you're doing a monomeric protein, and multimer obviously if you're doing a multimeric protein complex. Okay. The next step is I normally will always leave the database preset to the full database search. The only time you may want to change this is if you issue a job script to run AlphaFold2 on your target protein of interest, and you do a full database search, and you notice that it's taking forever because there's just a lot of homologous sequences found in either of these databases that it's searching, and it's taking too much time. You can probably run a reduced database without impacting the overall accuracy too much, right? Doing a reduced database search, if you go to the AlphaFold2 GitHub, will actually even tell you, running this may decrease model accuracy. So, you'll know when you want to change this. Okay. Outside of that, everything's ready to run, right? You can change this output directory if you so choose, right? You can name it whatever you want. Just try to rename it something that, if you come back to this in a couple months, it's kind of intuitive of what's in that directory. But outside of that, this is ready to run. So this will run the monomer PTM, no issue. Okay. Now, if I wanted to run the multimer model, there's really only a couple things I need to change. The biggest one, outside of this job script, is that your protein.fasta file needs to be a multi-FASTA file that includes every single amino acid sequence that belongs in what you either have prior knowledge on or are assuming is a multimeric protein complex, right? So we covered multi-FASTAs in class. If you don't know, you can Google it, search through lecture slides, things of that nature. Right. So the first thing we're going to want to do is change monomer PTM to multimer. Right. So it's going to execute the multimer model of AlphaFold2. There's a couple of other things we do need to change. Right. One of the biggest ones, right, is we need to remove one of the parameters listed in this code block here, and we then need to add another parameter. Right. And to understand which ones we need to add, we just come over to the AlphaFold2 GitHub page. And scroll down, it'll actually give us instances of examples of how to execute AlphaFold2 for the different models that you want to use, whether it's monomer or multimer, right? So keep scrolling down, we'll see a section called Running AlphaFold2. It explains the different models. And so here's an example. You'll notice it lacks the singularity command. That's because this is running through a Docker container instead of a singularity container, but regardless. So running this command above with the monomer model, and they're showing the reduced database would look like this. Right, so we have our FASTA path, we have our max template date, our model is monomer, our database preset is reduced database. Here it's able to just pull all of the information from the data directory. When we execute it on Grace, we have to declare all of these verbatim. That's why it's already been done for you in the monomer model. And then you also have to declare your output directory. Right. Specifically, if we come down to running the AlphaFold multimer model, it'll say you need to provide an input FASTA with multiple sequences, you need to set the model preset to multimer, and you need you need to run it with a couple of different changes. Right. An example that folds a protein complex multimer.fasta. Right. We see FASTA paths, max template date, and data directory. Right. Importantly, we'll notice that we need to remove the, let me just search for it here, it'll go much faster, right? These databases. So for the multimer, we need to supply a path called pdb seq res, right? And we have to declare where that is, and then we need to remove the pdb70 directory or parameter. So to do that, it's pretty straightforward, right? We're going to go to pdb70. We're going to do that. I'm just going to delete the line really quick. Right? It's pretty straightforward. And then I'm actually going to input a new line. Right? Quite easily, that's just going to be pdb seq res, right? I'm just going to double check to make sure I have this down right. Right, so we need to have a path called pdb seq res database path, right? This is what I need for my script, right? So go back to the tutorial, edit that file, and if I add it, it should look just like this, right? So that's pdb underscore seq res underscore database underscore path. Again, we're pointing to that download directory, which is where all of these databases have been downloaded to and stored on Grace. And then we're specifically declaring a further path just to say you go to the folder or the directory called pdb seq res and then specifically pdb seq res.txt, right? And that's it, right? Running this, the multimer model should work just fine, right? So we'll save and quit, and then we would issue the command sbatch run AlphaFold2.3.1 monomer.grace, and because I've made this the multimer model, just so I don't confuse the different scripts I have, I would rename this script to run AlphaFold2.3.1 multimer, if I can spell, multimer, we'll say no GPU, grace, right? Notice so the move command traditionally is used to move files or directories around, but you can also use it to rename, right? So now I've renamed it this run AlphaFold2.3.1 multimer, no GPU grace.sh, right? I also need to make sure I have a multi-FASTA file in here called protein.fasta, and then I can just execute this, and given however many hours it takes to run the program, I should have a nice batch of brand new predictions that I can go sink my teeth into, start digging in through the quality metrics, and start implementing that structure in either wet lab experiments and or further in silico analysis, right? So with that, I will see you guys in the next video.